Space itself is ringing from a distant collision, and the signal does not match what sent it. When two massive objects collide somewhere in the universe, the violence of that event does not stay contained. The collision compresses and stretches the fabric of space-time, sending ripples outward in every direction. Those ripples travel at the speed of light, crossing billions of light years without slowing, without dispersing in the way that light disperses, carrying an imprint of the event that created them. By the time they reach a detector, they are almost unimaginably faint, but they are there, and they carry information encoded in their shape. The shape of a gravitational wave is not arbitrary. It is determined by the masses involved, the distance between them, the rate at which they spiral together, and the geometry of their final merger. General relativity makes precise predictions. Given a known type of event, two neutron stars merging, two black holes colliding, the waveform should conform to a specific mathematical signature. The frequency, the amplitude, the rate of change as the objects accelerate toward each other. All of it follows from equations that have been tested and confirmed repeatedly in other contexts. Detectors measure these waves by monitoring the length of long perpendicular arms, several kilometers each, and tracking changes smaller than a fraction of a proton's diameter. When a wave passes, one arm compresses slightly while the other stretches. The instrument registers the difference. From that difference, the waveform is reconstructed. The waveform does not always reconstruct cleanly. Across a growing catalog of detected events, some signals carry features that do not fit the expected template. The mismatch is not catastrophic. The waves are still identified as gravitational in origin, still attributed to merging compact objects. But portions of the waveform, particularly in the final moments of a merger and in the signal that follows, diverge from what the equations produce. The divergence is small. It is also consistent enough across separate events that instrumental noise alone does not account for it. Space itself rang from a distant collision, and the sound was slightly wrong. The most immediate candidate for explaining the mismatch is the detector itself. Gravitational wave observatories are among the most sensitive instruments ever constructed, and their sensitivity is inseparable from their vulnerability. Seismic noise, thermal fluctuations in the mirror coatings, quantum noise from the laser light, electromagnetic interference from distant sources, all of these introduce artifacts into the data stream. Separating genuine astrophysical signal from instrumental contamination requires sophisticated filtering, and filtering always involves assumptions about what the noise looks like. If those assumptions are slightly incorrect, if the noise model used to clean the data does not perfectly capture the actual noise environment at the moment of detection, then features of the noise could be subtracted imperfectly, leaving residual artifacts that appear as waveform deviations. Alternatively, genuine signal features could be partially subtracted along with the noise, producing a cleaned waveform that is missing something real. Either pathway produces a mismatch between the measured signal and the theoretical prediction, without requiring any new physics. This is a plausible explanation. It is also one that cannot currently be confirmed or eliminated. The noise environment of a gravitational wave detector changes continuously. Seismic activity varies hour by hour. Thermal conditions fluctuate. The quantum noise floor depends on the laser power and the configuration of the optical cavities, both of which drift over time. Characterizing the noise at the exact moment a signal arrives requires extrapolation from measurements taken before and after the event. The shorter the event, the more problematic this becomes, and the final merger phase of a compact binary event can last only a fraction of a second. Multiple detectors operating simultaneously and independently can cross-check signals against each other. Genuine astrophysical waves arrive at each detector with predictable time delays based on the geometry of the detector network. Noise artifacts do not share this coherence. Coincident detection across instruments is the primary method for separating signal from noise, and it works well for the main body of a gravitational wave signal. For the subtle residual features that appear in the post-merger phase, however, the signal-to-noise ratio drops sharply, and the cross-detector validation becomes correspondingly weaker. The mismatch sits precisely in the regime where the instruments are hardest to calibrate against each other. What cannot be stated with confidence is whether the mismatch is inside the instruments or inside the physics. The second category of explanation concerns the source itself. General relativity's waveform predictions are derived from solutions to the Einstein field equations under idealized conditions. Two merging black holes are modeled as point masses in vacuum, with no surrounding matter, no magnetic fields, no asymmetries beyond those encoded in their initial spins and masses. Real astrophysical mergers occur inside environments. Black holes that have accumulated material form accretion structures. Neutron-star mergers occur inside the remnant debris of the stars themselves, surrounded by clouds of ejected matter moving at significant fractions of the speed of light. The interaction between the gravitational wave and this surrounding environment is not well constrained. Dense matter near the merger site can absorb, scatter, or re-emit gravitational radiation in ways that modify the waveform. The modifications would be small. Matter interacts with gravity weakly. But in the post-merger phase, when the source is no longer a clean pair of point masses, but a violently disrupted, rapidly oscillating remnant, the departures from idealized conditions are largest. Numerical simulations of these environments are computationally expensive and depend on assumptions about the equation of state of matter at extreme densities, assumptions that are themselves uncertain. Neutron star interiors, in particular, contain matter compressed beyond the density of an atomic nucleus, and no laboratory experiment has reached those conditions. The equation of state at those densities is unknown. Different assumptions produce different post-merger waveforms. Comparing a measured post-merger signal to a theoretical prediction requires first knowing which prediction to use, and there is no consensus on that. The mismatch may not be a mismatch at all. It may be a signal from physics the model was not built to contain. A third possibility sits between these two. The Einstein field equations have not been tested at the extreme conditions present in the final milliseconds of a compact binary merger. The strong field regime, where spacetime curvature is not just large but rapidly changing, where the gravitational wave itself carries enough energy to affect the geometry it is propagating through, is a domain where general relativity's predictions are extrapolated, not confirmed. The equations may hold exactly. They may not. Small deviations from general relativity in the strong field regime would appear precisely where deviations are observed, in the late stage and post-merger waveform, where the fields are strongest and changing fastest. Testing general relativity in this regime requires knowing what a deviation would look like before searching for it. Several classes of alternative theories of gravity make predictions that differ from general relativity in the strong field domain. Some predict additional polarization states, gravitational waves oscillating in directions that general relativity forbids. Some predict energy loss mechanisms that would alter the rate at which the wave's frequency evolves. Current detectors are not sensitive to additional polarization states in most of the detected events. The frequency evolution measurements are consistent with general relativity within their uncertainties, but those uncertainties are wide in precisely the late-stage regime where any deviation would be largest. No confirmed detection of a general relativity violation exists. The mismatch does not constitute one. But the gap between absence of confirmation and absence of deviation is wide, and the instruments are not yet capable of narrowing it in the regime that matters most. Each time a new event is detected, the same limitation surfaces. The signal arrives, the waveform is extracted, the comparison to theory is performed, and the late-stage residual sits outside what the model cleanly accounts for. Larger detector networks and longer observation runs accumulate more events, which improves statistical power. More events allow better characterization of the mismatch's properties, whether it scales with mass, whether it appears in all merger types or only some, whether it varies in a way that correlates with any known astrophysical parameter. None of these analyses have yet produced a clear answer. The sensitivity improvements planned for next-generation detectors will change the landscape significantly. Lower noise floors will allow the post-merger phase to be measured with higher signal-to-noise across a much larger population of events. Better detector characterization will reduce the ambiguity about how much of the measured signal is astrophysical and how much is instrumental. More precise waveform templates derived from more sophisticated numerical simulations will sharpen the comparison between measurement and prediction. Even with those improvements, the core of the problem remains structural. Validating a waveform prediction requires a reliable noise model. Building a reliable noise model requires understanding the detector environment completely. No detector environment is understood completely. The measurement always contains an irreducible component of inference, and inference depends on assumptions. The post-merger signal cannot be isolated from the instrument that measures it. The instrument cannot be fully characterized at the moment the signal arrives. The gap between what the equations predict and what the data shows cannot be assigned cleanly to either category until the noise model is unambiguously correct, and there is no independent method to verify that it is. Current physics stops at the boundary between the signal and the instrument. The waveform mismatch is not a small technical problem awaiting a calibration correction. It sits at the intersection of the most extreme physical conditions the universe produces and the limits of what any measurement apparatus can distinguish from the environment it operates in. General relativity may be exact. The surrounding matter may account for everything. The noise model may contain an unresolved systematic error. All three explanations remain open. The signal passed through the detectors. The instruments recorded something. What portion of what they recorded reflects the merger, and what portion reflects the detector itself, cannot be separated with the data available. Space rang. The exact note it struck remains unknown.